Hello and welcome to this video. Today we'll be talking about the virtual input output and the integrated logic analyzer, and we're going to do that by implementing this modified full adder in Vivado using VHDL, and we're going to use the ILA to be able to drive our inputs, to be able to observe our inputs and outputs. And we are going to use the virtual input output to be able to drive our inputs and retrieve our outputs. So as you can see here, we have a full adder and the sum and carry are being XOR and pushed to a register, and we observe them at the output. And we also have an inverter, which is simply inverting a signal at the rate of the clock. So what we're going to do is we're going to start by creating a project in Vivado, and I have already written the programs to this full adder, and we're just going to select them and then go next. And then here we're going to use our board, which is a ZCU 104 design cultural scale FPGA board. And then we're going to go next, and we are now going to get our test bench just to be able to validate our program by simulation to see that it's running well. And just before this, I need to make a few modifications on the test bench regarding the clock. Yeah, I think that should do it. Save and run simulation. Great, so it seems that it has run. So now let's see, we have our reset as 1 here and everything is 1. So in sense we're supposed to get let me see, so we are supposed to get 1 1 actually as our sum and carry. Let me just highlight this to be able to read it well, and yeah, you can see that we have 1 1. Now let's change our carry in a 0, and we're supposed now to get a 0 1 for our sum and carry, just to be able to make sure that our program is running well. And as you can see, yes, so we have a 0 1 as our sum and carry. So that means that our simulation is that our program is running fine. So now let's create an IP let's generate an IP by creating a block design. Now we can see that we have generated the design 1 there, and then we want to add our module, and we will add our top level module here, which is our full adder. And now we're gonna need to get our we'll need to get from add IP we get our ILA. Okay, let's get the VIO first. And for the virtual input output, you want to have all your output of your full adder to be the same as the number of inputs and of the VIO, and the number of outputs of the VIO should be equal to the number of inputs on your full adder. So now let's get the ILA. And for the ILA, you first of all select the native, and then you simply want the number of probes to be equal to the number of, whatever signals you're trying to observe. And we go on by connecting those. All our inputs to outputs, and we connect our probes. But for the clock, we're gonna have to get another IP here, because the clock of the ZC104 is it uses a differential clock for precision and noise immunity. So this IBAF essentially will be able to help us to connect to that differential clock of the ZC104. So what we do is we connect through all our clocks, and then we make this our top level design by going to right there and be able to make it as our external device. And we now validate it. It has validated. So what we do now is we want to create a wrapper. So we create a wrapper by right clicking on our design, and then we go to create a HDL wrapper. Right, so it seems like we have already created our HDL wrapper, and we can see it here, and you can see that you only have one input. Well, you have two clock inputs, but it's gonna just be one input that we will need to connect. So we go on now and run our synthesis. And this may take a while, so I'll just pause the video here and come back when it's done. So it looks like we have too many inputs and outputs, so let's see what's going on. Let's see, why do you have that? Yeah, we have our supposed to have only one input, so it seems like something is wrong. Okay, let me try and figure out. I think we'll need to have to set this as a top level. But let me first of all refresh this. I think we have to set this as a top level. Let me see. Okay. Yeah, we needed to set it as a top level, and after doing that, now let's see, we needed to set it as top level. Now we have to run our synthesis again. Run it. So when our synthesis is complete, we will need to set our clock, but here on the sheet it tells us that it is H11. However, in this general it tells us that it is F23. So we're gonna use the F23, and we're gonna have to select this as LVDS for our IO standard, and then we're gonna have to save this as on our XTC file, and then we're gonna have to run the implementation. And the implementation is done, then we have to generate our bit stream. So our bit stream is done. We're gonna have to now we're going to be deploying this on our ZC104 board, and this is it right here. So we've connected everything, and now we open our target, and we should now be able to program our device. And you can see here you have your .bit and your .ltx file, which is a bit file and the debug file. And after you do that, you should be able to see this window for ILA and VIO. We come here and VIO, we add all our pins, and we now select it. For example, for low it's red, and for high it's green. And for these ones we select as toggle pins, so that we'll be able to switch between 1 and 0. So we can see we have our sum, carry, and the not clock right there, which is the inverter. And here we will be able to see all these probes. And once again, this is our circuit, and we're going to observe our sum and carry, and also the not clock, which is an inverter. So let's see. When we put 0, 0, 1, 1, everything is 1, 1. We are supposed to get our sum and carry. See, this is our reset signal. When it's 0, everything goes to 0, and when it's 1, we are able to get our output. Okay, so let's test it a bit more. When we have everything 1, 1, our sum and carry becomes 1, 1, 1, and for 1, 1, 0, we get our sum is 0 and carry is 1. And we will also be able to observe the same thing here. When we have everything 1, 1, you see that we get our sum and carry as 1, 1 as well, and 1 XOR 1 gives us 0. So it seems like the circuit is working as expected even after deployment. So this is it. I hope you'll be able to follow this, and should be able to at least give you an idea on how to perform the VIO and ILA on your design. Thank you.